Okay. Hello everyone. Is previous class over?
Yes, sir.
Yes, sir.
Okay, fine. So we are talking about molecular docking. Can anyone define what is molecular docking? Not a particular definition, just what you have understood by molecular docking.
Like the process of interaction between target and ligand due
Hmm.
to the structure complementary and the chemical interaction complementary.
Okay. Okay, so some kind of interactions you are trying to measure between the target molecule and the pharmaceutical drug, and based on that you want to come to know like which one can be the best possible drug. For this, what you are exactly trying to estimate, like last time I mentioned, there are two things that your software should calculate. What are those two things?
It's free energy, sir. Enthalpy.
Free energy is correct. Any other thing other than free energy? Any other thing you want to say? Like enthalpy, you consider it's a part of the, sorry,
Position.
yeah, positions, or not just positions, we call it something called as poses. So for
Yes,
poses, we mentioned that orientation, position, and conformation, all the three things combined, it will be, we are going to call it poses. So your software should be able to determine the different poses, and for each and every pose, you should be able to determine the binding affinity. Then only you will conclude. So we talked about three different theories that you should know. What were those theories? The first theory was related to
lock and key theory.
Lock and key theory.
lock and key theory. There we said that the two compounds should be complementary in shape and size, right? Is it correct?
And chemical also.
Yeah, they should be also chemically also they should be complementary. Otherwise, there is no meaning. Just the two things will, even though they come closer to each other, they won't bind. Then the second theory was about
Induced fit theory.
induced fit theory, right? Even though initially they might not be have matching size and shape, but with after coming closer, they might have some conformational changes and there can be fitting. And the last theory was it
Conformation
was
ensemble.
yeah, conformational ensemble means a collection of so many conformations you have to consider for protein molecules, like not just by binding the protein conformation will change, but itself also protein conformation changes into so many types. So all these different aspects you should consider before you calculate the values of binding affinity. So this is what the detailed definition. Then I talked about you should find out different poses, and for all the poses, you should find out some score. So that score, you can even consider in QSR also you estimated some score. That score was your activity values, and then based on this score, here you are having the score as binding affinity. So using this, you are going to rank all those molecules, and you can say which molecule is the best one. Guys, is my voice clear or is there any are you feeling any
It's clear.
No, sir.
clear? So last time we mentioned that in the docking software, the two things are important. One is the search algorithm, how you are going to determine the poses, and the second thing is the most important thing that we should understand the criteria for our screening, and that is the scoring function. So I said the scoring function is nothing but the binding affinity, but how you are exactly measuring that. In the earlier QSR, you have developed some model yourself. Activity is the function of some descriptors. But here that what a delta G value you are going to estimate, how what it is dependent on, that you need to understand so as you can do the correct molecular docking. So last time I gave you this simple formula, delta G is equal to E complex minus the summation of individual energies of both the protein and ligand. So I said this is what nothing but is your score. Score means how you are estimating actually the delta G value. But if you want to estimate the score accurately, Okay, just a minute. I will just close one of my fan. It is noise. Just one. Okay. So I said this you can consider as your scoring function. Scoring function is a mathematical way you are going to calculate the delta G of binding. So this is looking a little bit simple. This you can consider in the simple form of you are having some energy of the complex, and from that the individual energies you are trying to remove. So this can be considered something like the enthalpic component. Now, what is the meaning of enthalpic component? Last time I asked you the question if there is a chemical reaction taking place. So normally in on the basis of delta H, whether it is positive or negative, you talk about something about the how the chemical reaction is happening, whether that is favorable or not favorable. Even that you can little bit comment on. So if delta H value is more negative, so you can say something about that exactly what is happening at the level of bond formation or bond breaking. So if it is more negative means you know that there is a more amount of energy is released. Means what? Is there more bond formation or more bonds breaking?
Formation.
More bond formation. Okay, so this is how you can consider it to be the how the energy is going to be released, and that's why you calculate as delta H as negative. So here also something similar can happen. You can talk about this process of binding, and if there is a bond formation is occurring, then what is going to happen? The delta H value should be negative. Right. Now, what kind of bond formation is there? Like when the chemical reaction takes place, you have some kind of bond formation and bond breaking, right? In this kind of protein and ligand, what do you think? What kind of bond formation are taking place?
Hydrogen bonds.
Yes, so that's what we had tried to talk about earlier. We are trying to talk about some driving forces, how the assembly is going to form, what are the driving forces for that. So ultimately, we want to say that our delta G should be negative and it is dependent on some of the driving forces like delta H, and there should be also some entropic factor that should come into picture. So out of this, you can understand first what is this delta H term that is going to contribute to your delta G. Like here, right now they haven't talked about any entropic component or something. So initially we'll just try to understand delta H. So delta H you should consider as some kind of bond formation or bond breaking is going to happen. And this is not some kind of your covalent bond formation or breaking what normally happens in your chemical reaction. In this case also there is some bond formation is happening, but these kind of bond formation are your weaker interactions, and these weaker interaction they play a lot major role in this kind of biological processes where the ligand and protein comes into picture. So what are those different weaker interactions will be there? So that will be similarly what you find in your water. So hydrogen bonds, van der Waals interactions, or electrostatic interactions. So all these interactions are what is going to happen continuously, like some of the group of your protein and some of the group of your ligand, they might be continuously interacting with each other. Maybe some of the bond will be permanently at the scale of if there are more little bit stronger electrostatic interaction or hydrogen bonds are there. So that might be some kind of little bit permanent formation will be there, but not as strong as your covalent bond formation. If there is some changes are happening continuously near to this complex, it might happen that these comparatively weaker interactions than your covalent one might break apart. Okay. So when you want to design some drug molecule, you want to make sure that whatever is going to bind to the receptor, it should not be a very weak binding. Otherwise, it will go attached to it, and then again it is going to detach. So it might not your receptor might not no longer it will remain active if you are going to make it active, or it won't remain more inactive if you are going to make it inactive. So this is what somewhere you are trying to going to control. So delta H. So apart from enthalpy, there is one more factor that you have to consider, and that is related to the entropy. And if you read this statement, they mention there is a difficulty with protein ligand docking. In part, it is due to that it involves many molecular degrees of freedom. Okay, this molecular degrees of freedom, there are so many, and this you need to consider properly so that you can ultimately estimate the proper delta G value. Now, what is this molecular degrees of freedom? Anybody has any idea? This in the bottom I have written the molecular degrees of freedom somewhere in 12th standard you might have understood. This is not that different degrees of freedom that you understand in the thermodynamics, but this is molecular degrees of freedom, not related to phase rule or something. It's a different thing. This is like how many number of ways a molecule, particularly in the gas phase, may move, rotate, or vibrate in space. This actually is talking about some kind of order or disorder. So if you see this molecular degrees of freedom, it is somewhat related with your entropic factor. What do you mean by entropy exactly?
Randomness of molecules. Randomness.
Randomness
Randomness of
in
system.
molecules.
Right. So randomness. So you might have till now heard about randomness, disorder, other things, but what exactly that how it is related to the entropy. So at the molecular level, you can actually visualize that thing. What do you exactly mean by entropy? How it is increasing? How the entropy is going to decrease? How the randomness is increasing, decreasing? So all these things. So for that, you need to understand the concept of this degrees of freedom. So I said degrees of freedom means how a single molecule, it is going to move, rotate and vibrate in a particular space. So if there are more ways it can do all these things, so you can say it is having more degrees of freedom, and more degrees of freedom means will be what? How it will be related with the entropy? If the molecule can achieve more degrees of freedom means what will happen to the entropy?
High entropy, sir.
The entropy will be more because the molecule is able to do freely whatever it wants to do. It is not restricted. Okay, more randomness. Yes. So you can see just this small video. What do you exactly mean by degrees of freedom? You can see there are three space coordinates x, y, and z. So in those three directions, it can move. So this is if it is able to move freely, that is means it is having more degrees of freedom. Then it can rotate. The diatomic molecule can rotate in two different ways, and then it can vibrate in along its center. So this is how generally they say at the if you go at the molecular level, a particular diatomic molecule will be having around 6 degrees of freedom. Similarly, if you consider triatomic molecule or other molecule, they will be accordingly having their more number of degrees of freedom. So why we are talking about this? Because we want to connect our calculations with this also. If we are able to understand if our molecules are properly doing achieving all these degrees of freedom, is they are going to have more entropy. Now, when we are talking about this docking also, we have mentioned earlier that there are some limitations. One of the limitations that we consider is actually it was related with your degrees of freedom, because like so many docking algorithms will be there. What they will do, they will be choosing they ideally they should choose the both protein and ligand to be flexible, so that what will happen, they will achieve all its conformational degrees of freedom. Means if you are going to make both of them flexible, like they are going to achieve all the conformational degrees of freedom whatever they want to do, and then that will be like more accurate kind of calculation. But you know that as the protein structure is very complex, I said that day we actually do not do this kind of calculation, because as per our current computational resources, this kind of calculations are very difficult. You might do it for a few compound, but not in as you are doing in the chemical informatics all the virtual screening for millions of compounds. So you need to have some kind of approximation so that you can at least do it for some 10,000 molecules or something at a time. So that's why we said we have these programs, but it is always there will be some limited conformational flexibility to the protein. And this is important to understand because all these things are going to decide how your delta G value will be evaluated. Now, there is one more factor. That one more factor is actually related to the solvent. Now, in your body, now what you are doing in your molecular docking, as you are seeing the structure, you are just assuming that there is a target and there is a ligand, and both of them are forming the complex, and you are going to calculate the delta G value. But is it going to be the correct value? What you are going to get if you are considering the only two components? Okay. So I mentioned that solvent also is something important, like whatever will be near to the ligand and even within this receptor pocket, even what they are going to, how they are going to act on to these compounds, even that needs to be considered into account. Now I said most of the time, the pocket that are formed, the receptor, what kind of nature these pockets have? In what kind of nature do these pockets have? Chemically, how are these pockets?
The hydrophobic.
Yeah, they are mainly hydrophobic in nature. Okay, like so many, we have seen that the hydrophilic group tried to expose outside, and the hydrophobic part tried to hide away from the solvent. So you can ideally consider that the hydrophobic compounds are there. So will there be any water molecules within this receptor?
No.
No, because the pockets are hydrophobic. So this is what like one of the important discoveries has happened in the last few years, that as the pockets are hydrophobic, actually we presume that there are no some any solvent molecules or something will be within the receptor. But with recent discoveries, they have found that even though the structures are hydrophobic, many times you can find out some water molecules inside the receptor. Now, why this is happening? This is one of the interesting question, and people try to answer this again at the level of like molecular calculations. But you can consider like I will try to talk about this in detail later on. Just right now, consider that when the two things are binding, so you are calculating just the interaction between body number one and two, but this is not a two body interaction, but you can consider there are even n number of factors, n number of molecules you have to consider, and everything interacts with each other. So most of the time the solvent molecules will be there. So if you want to accurately estimate the interaction between them, so all the interaction should be, their mutual interaction should be taken into consideration. But now you want to do the faster calculation on the computer for each and everything. So what they say, it is often ignored. You do not take into consideration the, you actually remove the water molecules even if they are these things you actually mere summation of all the various contribution to the binding. There are different factors, like you can say acid solvent factor is something that you do not take into consideration. You just have a receptor and ligand. So solvent contributions are somewhere removed from your actual calculation, right? So that you have to take into consideration somewhat in the implied way. This you won't actually calculate, but somewhat you have to write a empirical formula. Then there are some other things like delta G of conformation, delta G of something intramolecular you can consider, then delta G of rotation, delta G of translation, and translation you can consider, and delta G of vibration. So all these different factors are coming into picture based on what we have discussed earlier. So little bit we'll try to understand what are all these factors so that we can actually estimate the delta G of binding correctly. Now this is actually a more detailed formula for all your calculation. Different packages will be interpreting these things differently, and whatever will be your final formula, that will be dependent on software. Sometimes they ignore certain things, sometimes they take into consideration the thing. So some of the things we'll try to understand. I said the first thing that the software uh, actually try to calculate is the delta G of solvent. Now, what is delta G of solvent? I said actually there should be some water molecules also should come into picture, but that you actually ignore. So here actually all those solvent effects you need to consider. Means in reality what should happen, if in reality if you want to calculate this more properly, so you need to calculate the interaction of the receptor molecule with the water molecule plus the calculation of the interaction of your ligand with the water molecules, and also the water molecules will be also interacting with each other. So water water interaction, if you are able to calculate all these things properly, then only you are going to consider that all the factors you have included properly. But this doesn't happen, only you are out of these, you do not consider anything, you only what you are normally calculate, you calculate only the RL interaction, the receptor ligand interaction, and you ignore other things. So then what is the idea why you cannot calculate all these things, all these different things? Because if you take a big system like this, here actually you are assuming that we are having a simple system. But if you take a very big system where surrounding to this all the different solvents are there, another thing, so you can consider that how many times the interactions is going to increase, like everything is interacting with each other, so that is not possible for your faster calculation. So you have that, like in your case the most important molecule is your receptor, which is having a large number of compound, and as you want to focus on the ligand you can say, but you ignore rest of the thing. So they say that most of the docking calculation you are doing in the absence of any explicit solvent, means you do not consider any actual water molecule when you are doing the calculation. So it is important for you to devise the ways so that you take into consideration these important effects into the your calculations. So how people do this thing? Then this is done actually.
Sir, you are not audible.